Okay, and the last class we discussed Riemann integrable. So when we say a bounded function is said to be Riemann integrable, the upper integral and the lower integral should be equal. So quickly we recall what we discussed. Suppose f is a function from closed interval a comma b to r. Be any bounded function. This bounded function is very important. Bounded function. Now our aim is to find the area under the curve. Okay, so that is our main aim of this Riemann integrable. So when we say the function, so we have a partition P. Capital P is a partition. Partition is nothing but just a finite number of points. X naught. X naught is the A naught, A, and then X1, X2, etc. Xn is the another endpoint B. So this is a partition. Partition of the closed interval A comma B. Now for each partition, we define the minimum value of the function, that is mi. M suffix I is nothing but is a infimum of the function f of x, where x varies over the ith interval, that is x belongs to that xi minus 1 comma xi. In the ith interval, the minimum value of the function we call mi. Capital Mi is the maximum value, that is supremum of f in the ith interval, that is x belongs to xi minus 1 comma xi. Okay, now we define this delta r. So delta r is nothing but the length of the rth interval. So what is the rth interval? So okay, length is the endpoints. So xr minus 1. Okay, where r varies from 1 to n. So this is length of the interval delta r. Now we define the lower sum L of P comma F, that is lower sum of the function F with respect to this given partition P. For each partition, we define the lower sum. So the lower sum is nothing but summation Mi into delta I, where I equal to 1 to n. Okay. Now the upper sum. So this is called the lower sum. Lower sum of F with respect to the partition P. For each partition, we can define a lower sum. Lower sums are different if we give different partition P. Now we define the upper sum U of P comma F. Upper sum of F with respect to the given partition P is summation capital Mi. That is the maximum value of the interval, ith interval, into the length of the interval, where summation I equal to 1 to n. So this is called upper sum. Upper sum for given partition, upper sum of F with respect to the given partition P. Now, what is the relation between this? So before that, we define what is small m is nothing but infimum or the minimum value of the function in the entire interval closed interval a comma b. That is infimum of f of x, where x varies over the entire interval ab. Suppose x varies in the ith interval, that is mi. Okay, this small m. Capital M we define supremum of a function in the entire interval. So that is supremum of f of x such that x varies in the interval a comma b. Now there is a relation between this lower sum and upper sum. Lower sum is always smaller than upper sum for any partition P. Okay, and this is less than or equal to m times b minus a. And this lower sum is bigger than small m times b minus a. Okay, there's a relation between the lower sum, upper sum. Now, suppose this is for single one partition. Suppose you are varying the partition, you will get different lower sum, different upper sum. So you are going to take infimum or supremum of all the lower sum of partition P comma F. So for each partition, we can find a lower sum, and for that we have to take supremum of all the lower sum, such that here P is varying, where P is a partition, where P is a partition of the closed interval A comma B. For each partition, we can find lower sum, and then you have to take the supremum. We call this supremum is the lower integral. We denote integral A bar to B f of x dx. Okay, we call this a lower integral. Lower integral of f on the interval A comma B. Now, similarly, for each partition P, we define the upper sum, and then you take the infimum of the collection, where P is varying, where P is a partition. We take any partition of the interval, we can find the upper sum. So among that, you have to take an infimum. So we define denoted by A B bar f of x dx. So this integral is called upper integral of f on the interval A comma B. Now, if these two integrals are equal, then we say f is integrable. So now we state the definition. F is integrable on the interval A comma B if and only if the upper integral lower integral equal, that is A bar B f of x dx equal to integral A B bar f of x dx. So upper sum, upper integral, lower integral equal, and we call the common name integral A to B f of x dx. Then we say f is integrable. So simply we denote f belongs to the script R, sometimes called script R of A comma B. The script R is a set of all Riemann integrable, R integrable. So this notation R of close to A comma B is nothing but set of all integrable function or Riemann integrable function. Riemann integrable function, collection of all Riemann integrable function or just integrable function, Riemann integral function on the closed interval A comma B. So simply we can say f belongs to R of A comma B means what? F is integrable function on closed interval A comma B. Okay. Now we discuss some examples. All constant functions are Riemann integrable. So that is the first result we discussed. Any constant function is Riemann integrable. So any constant function is Riemann integrable. So Riemann integral means what? You can find the area of the curve. So any constant function is integrable, or simply say Riemann integrable or integrable. Now, more generally, any continuous function is Riemann integral. Any continuous function is integrable. Any continuous function is integrable. That is, lower integral, upper integral exist, both are equal. Integral means. And another theorem is any monotone function. So whenever we are talking about the integral function, that function should be bounded. Okay. So the next result is any bounded monotone. Monotone means either increasing or decreasing. So any bounded monotone function is integrable. Bounded monotone function is integrable. And any step function is integrable. There are so many results are there. Now these are all some important results. Okay. Now there are some properties are there. Suppose if you take two integral functions, sum of two integral function is integrable. Scalar product of integral function is integrable. All the things is there. We will discuss it later. Now we state some important theorem, that is summation of series. The theorem is called summation of series. So the theorem is called summation of series. So this is a very important theorem. Maybe many questions they ask from this using this theorem. So what is the first theorem says? The first theorem general for any interval a comma b. So what is the theorem says? Suppose if f is integrable on a comma b, if f is integrable, Riemann integrable or integrable, okay, integrable on the closed interval a comma b is given, then the integral a to b f of x dx value is nothing but limit n goes to infinity 1 by n or summation r equal to 1 to n h into f of a plus r rh, where this h is nothing but b minus a by n. Okay. Suppose sometimes they give the left hand side, sometimes they give the right hand side. So if the right hand side is of the form, we can write integral a to b f of x dx, and then you can easily find the value of this limit. Now the particular case of this, if you take the interval closed interval 0, 1. So maximum they ask the question, they take closed interval 0, 1. So what is that? So the particular case, if f is integrable on closed interval 0, 1, then the integral 0 to 1 f of x dx is limit n goes to infinity 1 by n, because substitute the b value is 1, a value is 1, a value is 0, 1 minus 0 by n, that is 1 by n. Since the summation independent of n, you can take 1 by n outside. Summation r equal to 1 to n. Now what is f of a plus h? So f of a plus r, here a is 0, okay, r by n, that is r by n. So f of r by n. Okay. So therefore limit n goes to infinity 1 by n summation r equal to 1 to infinity f of r by n. Then we can simply write, replace r by n equal to x. Okay, replace r by n equal to x. And then you have to take the remaining things, you have to put the integration there. That is, you have to put limit n goes to infinity 1 by n summation, you have to put integration 0 to 1. And then substitute r by n equal to x, we get this one. Okay. So this is very, very important formula, the second one. So whenever the right hand side we have this, we can simply write integral 0 to 1 f of x dx, provided f is integrable. Now we solve some problem using this. Okay. Exercise. Show that or find the limit. Maybe we can say what is the limit of limit n goes to infinity 1 by n times sine of pi by n plus sine 2 pi by n 3 pi by n and so on. Finally sine of n pi by n. We have to show that otherwise sometimes called what is the value of this limit. Okay. So first you have to write in the summation notation. So solution. So limit n goes to infinity 1 by n. So this can be written as summation k equal to 1 or r equal to 1 to n sine of r pi by n. Because if you substitute r equal to 1, you get the first term. If you substitute r equal to 2, you get the second term. Okay. Now by our case, so this is nothing but integral 0 to 1 sine of this r by n, we have to put x. Therefore, we get pi x into dx. So that's it. Now we know the integration of sine is nothing but, what is the integration of sine? Minus cos. Therefore, minus cos pi x by pi integration lower limit, upper limit. Now, therefore, you can take minus 1 by pi outside. Cos pi value is minus 1 minus cos 0. Cos 0 is 1. So that is minus 2. Therefore, minus 2 by pi. Therefore, you get plus 2 by pi. Therefore, the value of this limit is nothing but 2 by pi. Simple. Okay. So we will discuss one more problem. Okay. Next exercise. So find the limit n goes to infinity. Okay, 1 by n. 1 by n plus n square by n plus 1 whole cube plus n square by n plus 2 whole cube and so on, plus 1 by 8n. So what is the value of this? So we have to try to rewrite this into summation, limit n goes to infinity 1 by n into thing. Okay. Now we can write this is equal to, okay, solution. So this can be rewrite as limit n goes to infinity. So we can multiply and divide by n square for the first term. So we are going to multiply n square and then we are going to divide n square. Therefore, we get n cube. N cube can be written as n plus 0 whole cube, right? And the second term we can write n square by n plus 1 whole cube and so on. The last term, what is that? Again, we have n square is missing. Therefore, we got to multiply n square by 8 times n cube, right? So 8 n cube is nothing but what? 2n whole cube, because 2 cube is nothing but 8. But 2n is nothing but n plus n. Therefore, the last term we can write n plus n whole cube. Now write in the summation notation. Therefore, this is equal to limit n goes to infinity summation n square by n plus r what? Cube. We can put r equal to 0 to n. Okay. Now, what is the, but we need 1 by n before the summation, right? Therefore, we can take n cube outside from this denominator. Therefore, this is equal to limit n goes to infinity summation. So, summation r equal to 1 to n, r equal to 0 to n is not a matter. Okay. Now, n square by, you can take n outside. Therefore, we get n cube times 1 plus r by n whole cube. Now we can cancel n square. We get 1 by n. Since this summation is independent of n, you can take 1 by n outside. Therefore, limit n goes to infinity 1 by n. Summation r equal to 0 to n 1 by 1 plus r by n whole cube. Now this is of the form limit n goes to infinity 1 by n f of r by n. What is your f of x? 1 plus 1 by 1 plus x whole cube. Therefore, this is nothing but integral 0 to 1 f of x. What is your f of x? 1 by 1 plus r by n, we have to replace by x. 1 plus x whole cube into dx. Now, what is the integration of this? You take numerator, you get minus 3, therefore 2. Okay, so minus 1 by 2 times 1 plus x power 2. Upper limit, lower limit. So therefore, you can take minus 1 by 2 outside. If substitute 1, we get 1 plus 1, 2 square, that is 1 by 4. Minus substitute 0, we get 1. So that is minus 3 by 4, minus minus plus 3 by 8. Okay, therefore answer is 3 by 8. That's it. Okay, we will discuss one more problem. So because it's a very important thing. Exercise 3. So given any limit problem like this, you try to write in the summation format. Now limit n goes to infinity, n power n by n factorial power 1 by n. So what is the limit of this? Okay. Now we call the limit is L, and then we have to find the value of L. So solution, we call L is the limit of this. So limit n goes to infinity, n power n by n factorial power 1 by n. Now we need this 1 by n before the summation, right? Otherwise, after the limit, we need 1 by n. Therefore, take log both sides. Therefore, log L equal to limit n goes to infinity 1 by n times log of this. Okay. So log of n power n by n factorial. So n power n is what? We have to product n times divided by n factorial nothing but 1 into 2 into 3 into etc. n factorial. Therefore, we have a form this. Okay, and then n by 2, n by 3, and so on. Therefore, this is equal to limit n goes to infinity 1 by n log of the product of numbers, that is n by 1 into n by 2, etc. n by n. Okay, this is not n factorial, this is n by n. Now we know that log of AB is nothing but log of A plus log of B. Therefore, we can simply write the summation notation. Therefore, limit n goes to infinity 1 by n summation log of n by r, where r equal to 1 to n. Okay, but we need a r by n format, but here we have n by r. Therefore, what we have to do is nothing but 1 by x. Okay, so therefore, what will get? So we can rewrite this log of 1 by r by n. Therefore, simply we can write this is nothing but now we get our format. Therefore, this is nothing but integral 0 to 1 log of 1 by x into dx. Because r by n is x, but here we have n by r. N by r can be written as 1 by r by n. Therefore, 1 by x. Now, what is the now this is actually log a by b format. Now we have write log a minus log b. Therefore, this is nothing but integral 0 to 1 log of 1 by x is log 1 minus log x into dx. And we know that log 1 is 0. Therefore, minus log of x is 1 by x. Okay, 1 by x integral. So in 0 to 1. Now we get substitute the upper limit, we get plus 1, and then substitute lower limit, we get okay, I think, sorry, not 1 by x. Sorry. What is the integration of log x? X into log x plus x. Okay, that is differentiation is 1 by x. So minus integration of log x is nothing but x into log x plus x. This is the integration. Now 0 to 1. Now minus, you substitute 1, log 1 is 0. And then we have 1. Minus, if substitute 0, we get 0. Therefore, we get minus 1. This is the value of log L, but we need L, therefore this is nothing but log L. Therefore L is nothing but raise the taking e power both sides, therefore E inverse is nothing but 1 by E. So therefore, okay, I did any mistake? Log 1, that is 1, 0 is 0. Yeah, correct. 1 by E. So therefore this value is, we get to 1 by E. Okay. Now this idea. So given the limit, you try to write in the summation format, you will get the answer. This is very important thing. The Riemann integration, they will ask question from this. So even if you look at the, I think, the TFR question also, they ask this type of problem. Okay. Now we state the important theorem. When we say a function is Riemann integrable, if and only if we can find a partition P such that UP minus LP is less than epsilon for every epsilon. That is very important. Another theorem. This is a necessary and sufficient condition for integrability. So what the theorem says, a bounded function is integrable if and only if a bounded function f defined on the closed interval a comma b is integrable or Riemann integrable. Riemann integrable if and only if you take any epsilon, for every epsilon greater than 0, there is a partition P. There is a partition P of the interval a comma b such that the upper sum minus lower sum is less than epsilon, such that upper sum of f with respect to P minus lower sum of f with respect to that partition is strictly less than epsilon. Okay. For any epsilon, we can find a partition P such that the upper sum minus lower sum is less than epsilon, then we say f is integrable. Okay, this is another important theorem. Okay. Now we have a, I already said that continuous functions are integrable, monotone functions are integrable. Now we have some more theorem that suppose composition of one continuous function and one Riemann integral function is Riemann integral. Okay. So, and another one more thing is that suppose we have a function defined on a comma b. Okay, suppose f is defined on closed interval a comma b. Suppose if you take some point c in between a and b, then so what the theorem says? Okay, state as a theorem. Suppose f is integrable on a comma b, then f is integral on ac, the interval a comma c, and f is integrable on c comma b. The subinterval also is integrable. So if a bounded function f if integrable, bounded function f is integrable on the closed interval a comma b, then it also integrable on closed interval a comma c. Then it is also integrable on the small interval AC and CB also. Okay, and CB, closed interval C comma B, where C is the point in between A and B, where C is a point, where C is a point of this closed interval A comma B. Okay. Suppose a function is defined on the big interval is integrable, then it's also integrable for small interval also. That is the first one of the property. Now I already said that sum of two integral function is integral function, subtraction of two integral function is integral function, and then the integral value is nothing but sum of the separate integral. Okay. Next theorem. Suppose we have two bounded function f and g and integrable. Okay, that is actually called the integrability of sum and difference. So if f and g are two functions, both are bounded and are two bounded integral function. Bounded integrable function on the same interval on the closed interval a comma b, then the sum f plus g. So f is bounded, g is bounded, then f plus g is also bounded. Then you can take plus or minus. F minus g or f plus g is integrable, bounded and integrable. So the main important is integrable function. Integral function on the same interval a comma b. Now what is the value of this integral? So that is integral a to b f plus g of x dx is nothing but integral f of x dx plus integral g of x dx, a to b. Similarly, if you take minus, then you get minus a. Okay. Now, what about the product? Similarly, the product of two integral function also integrable. So maybe I stated this one, first property. Now second one is the product also Riemann integrable. That is f into g is also integrable on the interval a comma b. Okay. Now clearly the integral value is nothing but product of this one. Now similarly for scalar multiplication, suppose if you take some scalar c, then c times f is also integrable on the same interval a comma b. And then what is the integral value? C integral c times f of x into dx is nothing but c into integral f of x dx. Now next one is modulus. If f is integrable, then modulus of f is also integrable. Fourth point is modulus of f is integrable. If f is integrable, then mod f also integrable on the same interval a comma b. Then what is the value of this one? There is a relation modulus of integral a to b f of x dx is less than or equal to integral of modulus of f of x into dx, where a to b. So this inequality is very important. Modulus of integral is less than or equal to integral of modulus. Okay. And another one is what about the quotient? Quotient of two Riemann integral is integral, provided one function should be greater than or equal to something. So what about the next thing? Quotient. In general, quotient of two integral function need not be integrable, but only condition we have to assume that the one function there exists some t greater than 0 such that modulus of g of x, one function, is greater than or equal to t, is bounded, is not bounded above. So modulus of t is modulus of g of x is greater than t for all x in the interval close interval a comma b. Then the quotient f by g, because we need f by g is bounded. Therefore, g should be satisfy this condition modulus of g of t is greater than or equal to t for c. Now this is integrable. F by g is integrable on the interval a comma b. Okay, and bounded is because we are talking about integral means what it should be bounded. Now these are all important properties, and if you take the product, I already said the product. In particular, if you take both functions are same, then f square also bound. F square also integral. See, f belongs to of that is Riemann integrable on closed interval a comma b, then f square is also Riemann integrable on the interval a comma b. So these are all properties. Okay, and so for any doubt now.
No, sir.
Next, yeah, tell me.
No doubt, sir.
Okay. So the next important theorem is the mean value theorem for integrable. Okay. So, but we studied the mean value theorem for continuous function, differential function, but here mean value theorem for integrable. That is, we call as a first mean value theorem. Okay. So theorem, the theorem is called first mean value theorem on integral. First mean value theorem for integral. Mean value theorem for integrals. First mean value theorem for integral. So what the theorem says? Again, suppose f is integrable function and bounded. So if f is bounded and integrable, f is bounded and integrable function on closed interval a comma b, bounded integrable in the interval a comma b, then there exists a number mu, where mu lies between lying between the bounds of f. Okay, what is bounds? Actually, for f, we have upper bound is capital M because this is nothing but supremum of all the f of x, right? And then small m is the infimum of all the f of x. So suppose mu lies between this small m and capital M, that is the number mu lying between the bounds of f. So bounds of f means what? F have a bound, upper bound, lower bound. Okay, so what is this capital M? Supremum of f of x. And this small m is an infimum of all the f of x such that x varies in the closed interval a comma b. Suppose mu is lies between the bounds of f. So that is m is less than or equal to mu less than or equal to capital M, such that we can find a mu such that in between small and capital M, such that integral a to b f of x dx is equal to integral a to b f of x dx equal to mu times b minus a. So we can find a mu between small m and capital M such that integral a to b f of x dx is nothing but mu into b minus a. Okay, so this is the first mean value theorem for integral. It's very important thing. Okay, so integral function of integral is integral. So that is another thing that is very important. So now we move to the first fundamental theorem of calculus. Okay. Now you studied antiderivative, but anyway, so we define the integrability or antiderivative. Suppose f is integral function and bounded. So suppose f is bounded and integrable on closed interval a comma b. Okay, now we define new function pi or capital F. Okay, so actually this f is a function from closed interval a comma b to r is bounded and then integrable. Now we define new function capital F from the same closed interval a comma b to r. Okay, defined by f of, if you take any x here, is defined to be integral a is fixed. The upper limit is x. X is varying into f of some t into dt. So we are using the small f. We define capital F. Since f is integrable, therefore we can talk about the integral of f of t. So if f is not integrable, it's not possible. So the defining integral is not possible, right? It's not meaningful. So integral is, we define this is meaningful only when this f is integral function. Since given that small f is integrable function, using the small f, we define the capital F. The capital F of x is nothing but integral a to x f of t dt. Okay, this integral, this capital F, sometimes called indefinite integral of f, sometimes called indefinite integral, or sometimes called integral function. Integral function is very important function. So using the small f, we define the function that is called the indefinite integral or integral function. So what is the properties of this small f? Sorry, the capital F. Okay, so that is the fundamental theorem of calculus. So this capital F is always continuous function. We can easily prove that this is continuous. Okay, so how to prove this is continuous? So that is, we can use some epsilon delta definition to prove this is continuous. So that is, we got to find what is the modulus of capital F of x minus capital F of y. We have to prove this is less than epsilon whenever mod x minus y is less than delta, right? So this is the modulus of integral a to x f of t dt minus integral a to y f of t dt. Okay, now we can adjust this. Finally we'll get less than epsilon. Okay, so the proof is lengthy, but I'm simply saying that we'll get this epsilon. So therefore clearly this capital F is always in continuous, but we don't know it's an integral or not. Therefore this capital F is continuous function. Continuous function. The indefinite integral is always continuous. Okay. Now when this capital F is differentiable, only when the small f is continuous, because we don't know the small f is continuous or not, but we know that small f is differentiable, sorry, integrable. So integral function need not be continuous, but continuous functions are integrable. So we know that continuous functions are integrable, but converse need not be true. Continuous functions implies integral function. Okay, but the converse need not be true. So the integral function need not be continuous. So now therefore small f is not continuous. Suppose the small f is continuous, then capital F is differentiable. Okay. If small f is continuous, then the capital F is differentiable. Then capital F is differentiable. And what is the derivative of capital F? Is nothing but small f. Therefore, f dash of x is nothing but f of x. So the capital F is differentiable only the points where f is continuous. So suppose f is continuous at some c. Suppose f is continuous at some c, then f is differentiable only at that point c. F is differentiable only at that point c, and then f dash of c equal to f of c. Okay, suppose if small f is continuous at every point, then capital F is differentiable at every point. Then f dash of x equal to f of x. Okay, so this is actually a fundamental theorem of calculus. maybe I state thing. It's very important theorem, fundamental theorem of calculus. Okay, now I state that. So there are two fundamental theorem of calculus there. Now I state one. Anyway, both are equivalent. So different books state differently. So theorem. So the theorem is called first fundamental theorem of calculus. First fundamental theorem of calculus. What is the statement? Suppose let f is a function from closed interval a comma b to r be differentiable. It's given that it's differentiable. So differentiability means what? Is continuous always, because every differential function is continuous. So it's given that f is differentiable. Assume that f dash is, assume that f dash is integrable. Integrable on the interval a comma b. Then what is the integral of this f dash? Then because f dash is integrable, therefore integral f dash of x into dx a to b is nothing but just integration, summation, integration, and then derivative cancel. We get upper limit, lower limit. We get f of b minus f of a. The first fundamental theorem. Now the second fundamental theorem is nothing but the capital F. So theorem, this theorem is called the second fundamental theorem. Second fundamental theorem of calculus. So what is the statement again? Suppose f is a function from closed interval 0 a comma b to r is integrable. Be integrable, Riemann integrable function. Now the indefinite integral capital F. Then the indefinite integral. Indefinite integral capital F of small f is always continuous. Continuous. In fact, ellipsis function on this interval continues on closed interval a comma b, and the capital F is differentiable and is differentiable. So only when the small f is continuous. So differentiable at a point x if the small f is continuous at x. If small f is continuous at x, then capital F is differentiable at x. Otherwise, the capital F is not differentiable, but is continuous at x, but x in the closed interval a comma b. In fact, what is the derivative of this one? So, in fact, since f dash exists, because provided f is continuous, then f dash is nothing but small f of x. Provided f is continuous at x, otherwise this is not possible. If f is continuous at the point x. So this is the second fundamental theorem of calculus. These two theorems are very important. Okay, first fundamental theorem and then calculus, second fundamental theorem of calculus. Okay, so any doubt in this? So the only thing you should know, the capital F. So capital F is defined to be integral a to x f of t dt, where the f is integral function. This capital F is always continuous, but when the capital F is differentiable, only when the small f is continuous. Okay. If small is not continuous, then capital F is not differentiable. But capital F is always continuous. So these are the first fundamental theorem, second fundamental theorem. Now almost we cover the thing. So only thing we left this Taylor series. Okay, that is not that much stuff. We can simply write the derivative. Okay, so anyway, I leave it to that. Anyway, in the book you can find that the Taylor series formula. So just you remember that formula, and then any continuous function or any differential function we can write in the Taylor series. So maybe I can write the formula. Okay, Taylor's theorem. What the Taylor's theorem says. Okay, theorem. The theorem is called Taylor's theorem. The statement is, assume that f is defined on closed interval a comma b. Assume that f defined on closed interval a comma b to r such that all the derivative exist, all order, such that the fnth derivative exists and is continuous. Continuous on the interval closed comma a comma b, and fn plus 1th derivative exists, and f n plus 1th derivative, that is at a point x, exists on the open interval a comma b. Then if you fix some point x naught, fix a point x naught in the open interval a comma b, then this f of x can be written as, then for each x in x, then for each x in the closed interval a comma b with x not equal to x naught, there exists a c between this x naught and x, comma, there exists c between x naught and x, between x and x naught, such that we can express that f of x like this. So what is the important? The expression is f of x equal to f of x naught plus x minus x naught by 1 factorial into f dash of x naught plus x minus x naught square by 2 factorial into f double dash of x naught, and so on, plus x minus x naught power n f nth derivative of x naught by n factorial plus the remainder term. So plus x minus x naught power n plus 1 by n plus 1 factorial into f n plus 1th derivative of c, where that c is lies between x naught and x. So this is the Taylor's theorem. So given any continuously differential function f can be written as like this. So that is a special case for if you take x naught equal to 0, if you take x equal, that is x naught equal to 0, that the series is called a Maclaurin series. Okay, Maclaurin series nothing but you have to take x naught equal to 0, that is called a Maclaurin series. Okay, that is very important thing. Maclaurin. Maclaurin's theorem. So if you take x not equal to 0. So therefore, for example, if you take e power x, we know that the expansion of e power x is 1 plus x by 1 factorial plus x square by 2 factorial plus and so on plus xn by n factorial and so on. Okay, this is e power x is the Taylor series expansion, but you take x not equal to 0, we get a Maclaurin series. So similarly, if we take sin x is a continuous differential function, sin x can be written as what is that? Sin x is x minus x cube by 3 factorial plus x power 5 by 5 factorial and so on. Similarly, we define cos. So any continuous differential function can be written as the power series. Okay, so this is nothing but 1 minus x square by 2 factorial plus x power 4 by 4 factorial, all even powers. This is a Taylor series expansion of cos x about the point 0. So this is nothing but actually a Maclaurin series. Okay. So these are things. So only thing remaining is we got to find the radius of convergence. We will discuss in the next class.